So thank you all for joining. Good morning, good afternoon, good evening. And it's a delight to be with our friends, global friends, who are all interested in effective teaching and learning, student-centric teaching and learning. And this is a community that we have are building, started building with several webinars already. It has been a pleasure to have my guru, Richard Felder and Rebecca Brent, lend their names to this series, the webinar series. I'll let them talk for a bit before I'll first introduce our speaker for today. And our speaker for today is James Trevelyan. He has taught engineering for over 45 years. He has researched and observed engineering practice and what engineers really do, okay, in Australia, India, Pakistan, China, and several other countries. His books, Making of an Expert Engineer, another book, 30-Second Engineering, the third book, Learning Engineering Practice, are helping students and engineers worldwide. They're also helping to reshape engineering education. He's also a leading expert on robotics and artificial intelligence. He was awarded the Joseph Engelberger Award in 1993, the world's most prestigious award in robotics, for the development of sheep shearing robots in Australia. He and his students pioneered the Internet of Things in the 1990s. Most recently, James has become a startup entrepreneur, inventing and commercializing new air conditioning technology. His machines can provide affordable and sustainable cooling and for billions of people, okay? So his topic is very interesting and exciting, and we look forward to hearing from him. But prior to getting him to start his talk, I'd like to have my good friend and guru, Richard Felder, say a few words.
Thank you, Krishna. It's a pleasure to be here with you, and I'll add my voice to Krishna's in welcoming all of you. And we'll just say that when Krishna and Hans Hoyer and Rebecca and I first got together to talk about this series and how we might create it and what we hope to accomplish, one of the first things we said was we should get the people who have contributed the most to engineering education over recent decades. And we came up with a rather formidable list of people. And if you look at the roster of who is scheduled to talk, you'll see that they're all household words. But one of the very first names that came to our lips was that of James Trevelyan, who is a giant in engineering education. And I have been totally looking forward to hearing what he has to tell us about learner-centered teaching, which is at the heart of everything we're trying to do in this series. And so I don't want to take any more time from him. Thank you for coming to speak to us, James. And thank you, Krishna and Hans, for all the work you've done to pull this whole series together.
Thank you, Rich, and over to you, James.
Thank you. So let me share my screen and put the presentation slides. This is going to be a very conventional presentation, and there's quite a bit of material to cover. There will be a script as well as a recording on the Canvas website following the lecture. So let me start. So first of all, I have to say thank you, Krishna, for that kind introduction. It is a great privilege to be here and to have been invited to participate in this series, a great honor. I've long had a great admiration for Rebecca and Richard for so many years, and it was wonderful to see you both in Perth in 2011. And I do hope to be able to catch up with you face-to-face again soon. So today I'm going to talk about effective teaching and learning, and also about the social purposes of engineering. So this is where I'd like to start. I've got to go to the right application. First, I want to address our education objectives. What are we really here for? I'm going to give you some indications of engineers' performances, and I'm going to focus the talk particularly on India, but there are many other countries which this talk is relevant for, particularly low-income countries. I'm going to ask a simple question: is engineering the same everywhere? And I'll talk about models of engineering practice that have emerged from the research that I performed with my students, and of course, other people who've contributed over the last 3 or 4 decades, And I'll talk about ways that engineers use the maths and science that we teach. And finally, I'm going to suggest ideas that you all can try in your classrooms from tomorrow. Well, maybe not quite from tomorrow, but definitely they're ideas which you can apply without having to go to your faculty and asking for permission to change the curriculum. So I'd like to start with aspirations. Why are we here? I'd suggest we're here to help our students and their parents achieve their dreams. They've enrolled in engineering schools, so that dream for most will entail some kind of engineering occupation, perhaps even as an entrepreneur growing a new business. I've looked at the website of a professional tennis academy. And let's see how they talk about their students and their aspirations. This academy proclaims the well-known professional players that have graduated from it. How often do we see that in engineering schools? How often do we see on the school website a display of alumni, some famous and others not so well known? Their biographies. Where did they go after they graduate? These things are important because they're celebrations of success. And you know, I don't see that very often in engineering schools. In fact, the performance indicators suggest that our teaching and learning engineering is not as good as it could be. So here we go. Here's a pertinent question. And thank you, Krishna, for inviting me to India just a few weeks ago, because this question came during one of my talks. And the question was from a faculty member of a college in India who asked, why do we need to rethink engineering education in this country? Surely, Indian engineering graduates succeed in countries like the USA and Australia. Doesn't that confirm that Indian engineering education is succeeding? That's a very good question. Now, I was employing engineers in Pakistan and my hair turned gray with frustration. My wife facetiously suggested that these engineers were taking revenge for colonial occupation by some of my ancestors. Visiting India, I learned that engineers faced the same challenges as in Pakistan. Clever, capable engineers struggled to achieve the same results that they could deliver in my home country. I'm going to focus on India in this talk because so many of you live and work in India, and you all share dreams of future prosperity for your country, wherever you are. So let's start on this slide with a recent paper by Tilak and colleagues who pointed out that a large percentage of Indian engineering graduates are effectively unemployable, particularly in civil and mechanical engineering. It doesn't take much research to find out that Indian engineering graduates' starting salaries are about 1/10 that what you would find in the USA. Economists would point out that that is a strong indication that they cannot provide the same kind of value for their employers as engineering graduates in America or Australia. My research interviews revealed that many engineering graduates find work as programmers after a short training course, and they get paid considerably more than they would have as engineers. And again, economists would say that shows they are generating more value for their employers because salary is an approximate indicator of value generation. And it tells us that engineers produce more value as programmers, an occupation for which they received minimal training, compared with working as engineers, for which we have struggled for perhaps 4 years or more to provide them with a sound education. There's some red flags there, definitely. Vinay Domal, one of my PhD students, wrote a wonderful thesis doing extensive field studies in Indian manufacturing plants and in Australia, and found that novice engineers employed in the Indian factories were essentially completely unprepared for their work, which was typically as production supervisors. All these are red flags, and they're telling us that we do need to think carefully about engineering education. I suggest that we are really only succeeding as educators if all of our graduates can achieve their dreams in their home countries. If our graduates have to leave and never return, what's that achieving for our grandchildren? With Vinay and my other students, we completed somewhere around 350 interviews.
Yeah. Commitment on the
and a dozen or so field observations of engineers at work, and several other people have studied engineers in the last 20 years, following pretty much the same lines of research. So, what is it that engineers really do? This is the best way that I can summarize what we found. It tells us that engineers are people with specialized technical knowledge who conceive, deliver, operate, and sustain artificial objects, systems, and processes that enable people to do more with less. Less effort, less materials, energy, uncertainty, health risk, and environmental disturbances. And that really amounts to this. Engineers enable people to be more productive. Think about it. Thousands of years ago, engineers delivered irrigation systems, roads, and city walls for security. These days, telecommunications, transport, buildings, water supplies, sanitation, and so much more. Since the dawn of time, engineers have delivered artifacts that enable people to do more with less effort. Now, productivity isn't everything, but as Krugman told us in 1990, a country's ability to improve its standard of living over time depends almost entirely on its ability to raise output per worker. And productivity, particularly producing goods with far less materials and energy and environmental disturbance, is critical for sustaining life on this planet. So how are we improving productivity around the world? There's some other indicators here which should raise more red flags. This graph summarizes data from McKinsey in 2016. What it tells us is that productivity in the US was about 10 times that in India, 5 times that in China. China today probably lags the US still by a factor of 3 or 4. And remember, Indian engineering graduates are earning 1/10 as much as USA graduates. The productivity data here would predict that, because engineers are intimately associated with productivity improvements. The data also tells us, not the data on this slide, but in the McKinsey report, that only a tiny handful of countries, 3 or 4 at most, have transformed themselves from being low productivity, predominantly agricultural subsistence economies into advanced post-industrial economies in the last 7 decades. And all of them are special cases. You can ask me about that later. So what does low productivity mean for ordinary people? The answer is high costs. Here, drinking water, we take it for granted. In Perth, one of the driest cities in Australia, in the driest continent, water is delivered to homes at $3 per 1,000 liters, including the cost of the connection. And across South Asia, you'll see women carrying water or water being carried on trucks. The cost delivered is $35 to $50 per 1,000 liters, many times more than in Australia. And most of the cost is in the value of time used for unpaid labor. Economists will give you simple formulae to calculate that. And what that means is that safe drinking water is simply unaffordable for vast numbers of people. Around 3 billion people on the planet drink unsafe water every day. And as a result, about 45% of children across South Asia and Sub-Saharan Africa are growing stunted due to fecal contamination. And that is an unbelievable care burden on future generations. These children will never develop fully as adults. Here in Jakarta, in Indonesia, water delivered in familiar 20-liter bottles. The cost delivered around about $100 per 1,000 liters. And compare those costs with Australia, $3 per 1,000 liters. Now, when a commodity, which is absolutely essential for human life, costs so much, no wonder economic and social development is difficult. And water supply is definitely engineers' business. We are not succeeding with the most fundamental business on the planet, getting safe drinking water for people. And remember this, low productivity means high real costs for goods of equivalent quality, durability, reliability, and performance. This is not just an issue in low-income countries. Take a look at this graph. This shows us manufacturing productivity, and noticed how it collapsed after the global financial crisis. This data comes from the US Bureau of Labor Statistics. Manufacturing productivity grew at about 3% a year until 2007, and since then, it has been growing at a crawl. I can't help noticing that it was in 2005 that the smartphone appeared. Is that just a coincidence? Or does the smartphone have something to do with this collapse in productivity growth? I would argue that it definitely does. And that's an interesting discussion we could have at the end of the talk if you really want to go there. And what are the consequences? Sorry. They're very significant because when you get low productivity growth, then wages stagnate. People don't get the improvements in their living standards that they had become accustomed to over earlier decades. And they get angry and elect populists like Donald Trump. And the resulting political stability, not just in the US, has been extremely serious and continues to be serious in many countries today, including where I am here in Islamabad in Pakistan. Now, the next question, is engineering the same everywhere? Well, you would think it was. That's what the accreditation criteria imply. The Washington Accord has been ratified by 29 countries across the globe. And we have accreditation agencies like ABET, the Indian National Board of Accreditation, Engineers Australia, the British institutions, and so on. The assumption here is that the essential attributes of engineering graduates are universal, and they've been published by the International Engineering Alliance. You can find it on their website. But I would argue that engineering is not the same everywhere. Here, this picture shows construction in Australia on the left and in Pakistan today on the right. You can see that this is quite different. Okay, in some respects, it's very similar. We've got reinforced concrete construction. But there's enough here to show you that engineering is significantly different. And this is a very superficial flag-raising exercise to say that engineering is not the same in these two countries. And all the results I've shown you so far in terms of, say, starting salary, employability statistics, and so on, they should tell you that engineering is not the same, because with engineering education largely standardized around the world, and yes, engineering, there are minor differences in the education, but if the engineering is not the same, it's because the graduate this should tell you that engineering is not the same, because if graduate outcomes are starkly different between, say, the USA, Canada, Australia, Europe on the one hand, compared with India, Pakistan, China, Bangladesh, and other countries, then that's telling you that engineering is not the same. The place the graduates go does not match up. But we need to think very carefully, because this is not necessarily just an education issue. If we take results from occupational sociology, we can identify several factors that tell us how competently people perform at work. Innate abilities are extremely important. Physical attributes like how strong you are and general intelligence. Over the last 20 or so years, learned abilities like emotional intelligence also have been found to play a significant part in workplace performance. And certainly education, providing people with skills and knowledge, is extremely significant. We can never get away from that. The systems and physical infrastructure in the workplace have a huge impact, as I'm going to show you in the next few slides. And another one is processes, how people do what they do at work. And these can be formal procedures or informal ways of working. And then culture. Bourdieu tells us about the word habitus, habitual ways that people interact in fields. Fields being places like workplaces, schools, family, political environments. And it's this that defines culture. Sociologists describe this in 3 words. Oops, the 3 words disappeared, but we'll come across them in subsequent slides. Now I want you to have a look at this slide. What we see here is a street market. And I want you to compare this with the next slide, a supermarket. So what we see here is a very different set of physical infrastructure. What's happened here is that the combination of the checkouts, the physical infrastructure, the barcodes on products and shelves, the shelving itself, the displays, the packaging, and the logistic systems that goods delivers when they need it, and so forth. These are the things that make a bunch of school leavers productive in a supermarket. Whereas if they were in the street market here, it takes decades of experience before you can start earning a reasonable living, including things how you lay out the fruit, where you get the fruit from, where you position your stall in the market, and so on and so forth. So this is just to show you that physical infrastructure has an enormous impact on productivity at work. So we have three words that describe this in sociology. We have systems. That's the ways of working. We have the structures, the things that people can't change. And we have agency. Agency describes what individual people can decide for themselves. In the case of the supermarket, physical infrastructure constrains agency. But the advantage of constrained agency is that you get high productivity and low costs. Now, I want to show you about these pictures because this story actually came from one of my graduate students observing engineers at work in India. This is not an actual photograph of the site, by the way. In your mind, picture an engineer standing beside the road at 7 o'clock in the morning with a map in her hand. And she is directing this gang of workers to dig because hidden under the ground, there is a suspected illegal connection to a nearby house. There's about a dozen guys with picks and shovels, and they get to work. She returns at about 3 o'clock in the afternoon. The footpath and the road has been dug up. The traffic is gridlocked. Her phone is ringing continuously with important people in the district who all have their phone number harassing her to try and find out what's going on and when the road is going to be restored so they can get back to their homes and get their goods delivered. At 3 o'clock in the afternoon, despite this long trench, it's quite obvious that there's no pipe in sight. Contrast this with digging a hole in the road here in Britain. Picture in your mind the engineer again at 7 a.m. in the morning with her map. A contractor arrives with a digging machine. The engineer directs the contractor to dig up the road and check for unauthorized connections. But there's a big difference here, and it's not just the machine. The contractor says, "Oh, no, here's another totally ignorant engineer. Listen, ma'am, the pipe is simply not there. Can't you tell? It's over there," pointing to a slight subsidence in the road 20 meters away. Now, the Indian gang of laborers already knew where the illegal connection was because they earned some extra cash installing it. But it would not have been worth the risk of losing their jobs to tell the engineer that she didn't know what she was talking about. So they kept quiet and dug the hole where they were told. They knew it was not where the engineer was directing them to dig, but the culture meant that they couldn't tell the engineer to her face that she was wrong. And so we can see here in this simple illustration how culture interferes with the exchange of information. And that's crucial with what is to follow. So let's talk about models of engineering practice. What exactly do we see happening in engineering workplaces? Well, one of the things we see is this. We see people interacting with physical objects. And this, by the way, this is work of occupational sociologists in the 1990s. We also see people interacting with abstract objects, and these days predominantly through computers. But computers are not the only means for doing this. And the third thing is we see lots of people talking with each other, and particularly in engineering workplaces, most of the conversations have a technical flavor to them. Now, if we think about professional engineering work, and you think about those three groups of occupational categories, that is manual manipulation of physical objects, cognitive interactions with abstract objects, and socio-technical interactions with other people, I'd like you now to write down what you think the percentages are. And if you think there's something else that's not being covered there, Write that down too. So I'll give you 2 minutes to do that, and it'll give your minds a little break. So get your pens and pencils out and start writing. You can write 3 percentages or 4. These, by the way, are all photographs of actual activity in engineering workplaces. They're not synthesized. I think perhaps 60 seconds would be enough to write a maximum of 4 numbers. Gee, that's clever. Somebody's managing to write on the screen. How are they doing that writing on my screen, Krishna?
There is an annotator that they can use, and I'm trying to figure out how to stop
Well,
them.
that's brilliant. Well, it's good because I always learn something from
You
my
want to
students.
let them do it? They scribble nonsense.
Go
also.
ahead and do it.
They might
Yes.
scribble nonsense also,
Scribble.
some of them.
Exactly.
At least
Go
this
ahead
person is giving you some good information.
Yeah, keep doing it, please. Oh, no, don't rub it out.
Yeah, I'm not interfering with the progress, but I guess that's clever. Yeah.
All right. Well, thank you for showing me that. And afterwards, you can explain to me how you did it. All right.
There's some chat. Some people are putting in the chat. You can see it if you want, or can you see the chat?
All right. Enough time.
Okay.
Well, what percentages did you write? What the research shows is that professional engineers spend most of their time on social interactions with other people. They spend very little time on hands-on work and a little on cognitive interactions with abstract objects. As one engineer described to me, he said, I always get frustrated at work because I never get any opportunity to do things hands-on. So that's why everywhere I go in the world, I take a 20-foot shipping container and it's full of my machine tools and my materials. And I do that in my spare time. So this explains why so many engineers get frustrated, because they see the group 2 work, interactions with abstract objects, as real engineering, design, calculations, modeling. It's the stuff I learned in school, they say. And when engineers talk about social interactions, they will often say, oh, look, it's all non-technical. It's just discussions, contracts, negotiations, meetings, admin stuff, emails. And as one engineer said in one of my interviews, random madness. So here's a summary, some numbers for you. What does it tell us? Have a look at that just for a minute or so. So it tells us that engineering is predominantly interdependent work. A wonderful word from Casey Beddoes. Engineers have to collaborate with others because all the artifacts that are the products of engineering, the artifacts only appear through the work of people who work with their hands and people who work with keyboards. What was really surprising for us was that the 60% plus or minus 20% is almost invariant with experience, even for engineers straight out of school. They're spending most of their time interacting with other people, not just necessarily face-to-face, it can be asynchronously by emails, reports, and so on and so forth. So the question was, why is it that socio-technical interactions and collaboration form such a large part of professional engineering and are seemingly in that proportion is seemingly invariant with career level? What's going on here? So I'm going to give you an explanation, which has come from my research, but you're welcome to put up other explanations as well. So let's look at the knowledge that graduates acquire in engineering schools. And this slide summarizes it. Prediction, their ability to predict doing forecasting, simulations. They know quite a bit about material properties, characteristics, models of engineering products and materials. And of course, they've gathered quite a bit of abstract science and mathematics knowledge. They also know how to operate software, and they can usually write reports. Let's put that in context. This is a map of the kinds of technical knowledge that engineers use in the workplace, identified from our research studies and those of others. And here's a map of organizational knowledge. Incidentally, I use clouds as a symbol for areas of knowledge because they capture, I think, the important aspects. First of all, they're fuzzy. It's very hard to define the edges of a cloud. But the thing I like most is that the further you get into a cloud, the less you can see everything else. And this is so true of specialized knowledge. The more that somebody specializes in a particular domain of knowledge, the harder it is for them to see everything else. It's so easy for us to fall into that trap. Come back to technical knowledge. So here's our young graduate. How does she get to know all this stuff? Does she spend a lifetime trying to learn it? No, because she needs it straight away to do her job. Of course, in reality, we find that she's working with a bunch of other people. And these people have expertise in different areas that they've built up over time. And people talk with each other. So our graduate at the center, her social network is acquiring knowledge from these other people. But the knowledge transfer depends on the strength of the social relationships, here represented by these solid lines. And one of my students suggested this wonderful analogy, that it really is a network of pipes with valves. And each pipe has a valve between each pair of people. And that valve can be opened or closed by either person. So the knowledge transfer depends on the strength of social relationships. And so the knowledge flow depends on the relationship between each pair of people. And this is of critical importance because building relationships at work is the key to accessing technical knowledge. In other words, the technical knowledge that lies at the core of engineering is actually a social network. It's accessed through a social network. And as we have seen, culture influences how easily that knowledge flows across the network. Now let's get back to what graduates learn. And here's another model. Another way of portraying engineering practice. And we see here that it's based on 3 pillars. On the right-hand side, we see what engineers learn in school, the engineering, and hopefully a bit of business science. But it is possible for them to pick that up later. Communication skills, which we so often talk about in terms of output skills. Unfortunately, we seldom think about listening, reading, and visual perception. But these are of critical importance, far more important. And then thirdly, symbolically, largely hidden, what I call tacit ingenuity. This is the ability to come up with solutions when they're needed. And these 3 pillars support a platform which I call technical foresight and planning. And the slices above are the ways that we see engineers working with others, learning from others, teaching others, coordinating the work of others, project management, which is essentially managing uncertainty caused by people, and multi-stakeholder negotiation. And when all of this works, there are 3 forms of value that are generated, and I symbolize them with cups of tea because my wife is a tea addict. I learned early on in my marriage that life is measured by the number of cups of tea that one receives. So we have client satisfaction, which is crucial because satisfied clients pay their bills. We have achievement satisfaction, which is when you tell your children and your grandchildren, and you say something like this, you see that funny little bit up on the right-hand side that sticks out? I designed that bit. And then thirdly, reputation. Engineers' reputation is ultimately what brings them work. And we see through all of this, the thread of technical stuff, the blue lines and wavy lines that ties it all together. This is what distinguishes us as engineers, even though it's largely a social profession. So here's engineering, what we focus on in school and education. And here's the rest. And I argue that we don't pay enough attention to the rest. And that's why our students' grades don't make any difference in actual practice. It's all that other stuff as well that makes so much difference. to their workplace proficiency. And what does this mean for engineering education? Does it mean that we have to switch entirely and spend only a small proportion of time on maths and science and spend much more time on communication? Absolutely no. And for good reason. But I do want to point out something that I think is very significant. If we look back at this diagram and identify where we focus on in engineering education, we can see that it's the solid green circle on the left-hand corner. So we see that here, engineering education focuses predominantly on group 2 work. And that's why engineers call that real engineering. That's why they get so frustrated when they find that most of their work involves group 3, socio-technical interactions. So now, of course, we have to focus on the engineering, science, and maths. And I'm not questioning that at all. What I am saying is that we do need students to realize that when it comes to engineering work, they're going to be involved in a lot of social interactions with other people. And much of that social interaction will be about getting access to the technical knowledge that they need to do their work. That's really all I'm saying. What we can build on here is that it's really no different in engineering schools. Engineering education is a socio-technical process. We spend lots of time talking with our students, and they talk with each other as well as they struggle with their assignments. So the socio-technical content in education is similar, both in school and engineering workplaces. We just need to point that out to our students. And here's another difficulty. For about 20 years, perhaps a little longer, engineering education has essentially been enslaved to the idea that we have to demonstrate that graduates have certain competencies. Now, there's nothing particularly wrong with the idea of competencies. They have become well established in human resources practice. The difficulty, particularly in engineering education, is that we as teachers have only a vague understanding of what our graduates are expected to do in practice. So let me give you this example. 3 short sentences. Sally cut the cake. Vijay cut the grass. Bella cut the cloth. Okay, so it's pretty obvious, isn't it? Sally cut the cake with a knife, as we can see in the picture. It's also pretty obvious that Vijay would have cut the grass with a lawnmower, and Bella would have used scissors to cut the cloth. But what if Sally had used a lawnmower to cut the cake? Yeah, we can all laugh. But there's nothing in these sentences that tell us which tool Sally would have used. We rely on our implicit, tacit knowledge of the work and our experience of life to know that one cuts cake with a knife, not a lawnmower. So it's this implicit, unwritten knowledge that is the key to understanding competencies. But if we don't know what engineering really involves, how do we as educators convey to students all this unwritten, tacit knowledge that we don't even know ourselves? In other words, how can we educate engineers without understanding how novice engineers are expected to perform? Competencies can only be interpreted if you know what the work involves. So we have to realize that we need at least a basic knowledge of what engineering work entails. And that's what I'm trying to do in this talk. So now I'd like to jump a little bit and ask this question. How do engineers use the maths and science that we spend so much time teaching? Well, this is a really interesting question. I'm sure that we all share a common apprehension. Certainly I have for many years. Most engineers, if you ask them, will say, well, I can't really recall any of you that using any of that maths and science stuff that we learned in college. Partial differential equations, vector calculus, Navier-Stokes equations, Lyapunov functions. We teach them, but do students ever use that stuff? I've been in research and development for much of my career as a professional engineer, as well as a teacher. And I wrote a lot of software for robots. But did I ever seriously use the Lyapunov functions? No. So what does the research tell us? Do engineers really use the maths and science that we teach? Well, Yes, they do, but not directly. Of course, it's embedded into so much of the software that we take for granted these days. But as engineers, we use it much more in a tacit sense. I speak here as a practicing engineer. We make countless daily decisions in a split second without ever realizing it. And many of those decisions rely on an instinctive knowledge of science and maths. So tacit knowledge, it's critical here, but what is it? Tacit knowledge is knowledge that we're unaware of. So for example, the language, the meanings of the language, the meanings of the words that we use, how we interact with other people, riding a bicycle. Have a look at this picture on the right-hand side of a construction site. Where does the crane go? In fact, practically everything you can see in this photograph is not shown on the drawings of the buildings. All that temporary work, the scaffolding, the stores, the materials, they're placed on site as a result of the implicit knowledge, tacit knowledge in the minds of the construction crew, the false work in order to make the construction feasible. So engineering relies extensively on tacit knowledge acquired by experience in the workplace. And it turns out, thanks to the work of Eileen Gould in Ireland, that engineers use science and maths in most cases in a tacit sense. For example, we instinctively know that the gradient is 0 at the maximum and minimum of a curve. And we know that from endless practice sessions doing mind-numbingly boring practice problems. So we get to be able to apply that without even thinking about it. And then we say, well, how do we acquire tacit knowledge, since it's knowledge that we're not even aware of? Well, the answer is practice. Here's how we acquire the tacit knowledge of riding a bicycle. So what this means is that all those practice problems that you get students to do, boring in many instances, they're all building up that tacit knowledge of maths and science, which is the way they're going to apply it in the workplace because they won't have time to use the formal techniques. So keep those practice problems coming. It actually does work, and students actually use it, but without any conscious awareness. So in the last part of this talk, I'm going to take you through some techniques which I have used in my classes, and I'm going to explain how they're based on engineering practice research. Essentially, what you can do is you can change the context in which practice problems are made available to students. I'm going to explain how you can adapt these ideas to make teaching more fun and rewarding and help your students follow their dreams, whether it's in India, Pakistan, Bangladesh, or anywhere else. So first of all, what is it that engineers do? Why do they do what they do? Engineers, as I said, engineers are people with specialized technical knowledge and so on. And that's what I think where I think this definition could be so useful for you, because in explaining that engineering is really all about enabling people to be productive, you give engineers, graduate engineers, a reason for their work. So much of the time in engineering schools today, we talk about engineers solving problems. But the difficulty with that explanation is that everybody solves problems. Think about it. When you're trying to get to work on time to give that lecture by public transport or by car or whatever transport you have at your disposal, what you're really trying to do is to minimize the time it takes and to maximize your chance of finding an appropriate parking spot or for your bike or your car. And that's problem solving in a constrained technical domain. Cooks do the same thing, preparing a tasty meal with whatever they find in the cupboard and the refrigerator. So thinking in terms of productivity, here you're providing the social reason for engineering. And I'm deliberately not talking about this in financial terms. That's why I suggest explaining that engineering enables people to be more productive, to do more with less effort, time, materials, energy, and uncertainty and risk and environmental disturbances. It's simple, you can easily do that. The next thing is to explain engineering teams. Yes, all engineering relies on people with their hands on and people who operate engineering systems. But we also need people who can coordinate that work while preserving the technical intentions behind any given project. And this is what professional engineers do, making sure that those technical intentions are preserved when technicians do their work, when drafters do their work, when programmers do their work, and so on. So, explain these three aspects of engineering work just so that students have a more realistic expectation about how they fit in. And then they'll learn to see that social interactions are going to be a real part of what they do. In other words, I'd like you to try and get them to see social interactions as real engineering work, rather than just something they have to do. And thinking that group 2, the cognitive interactions with abstract objects, is real professional work. Well, yes, it is. But the important thing is it's only a small part of what they'll be doing. Now, next, something that's critical. Explain engineers' earning potential, because a lot of students enroll in engineering with the idea that they're going to get a reasonable salary at the end of it. So explain that earnings over time are proportional to value generation. This is a fundamental principle in economics. And value generation implies the following activities: creating value through good service, differentiating products, and reducing the perceived risk in the minds of investors. Delivering value through effective coordination, keeping on budget, shaping expectations. And lastly, protecting value through safe operations, maintenance, environmental protection, and co-creating value with communities. You can find all this in my book. And ask students to figure out where engineering skills are most needed. And here's the most important thing. Explain that what research demonstrates is that engineers' earnings in their home country can exceed their earnings elsewhere. In other words, if you're in India as an engineering graduate, you don't have to travel to America to earn a great deal of money if that's what you really want to do. But the key to it is knowing how to deliver value for your employers and your clients. Next, listening. Let your students measure their own listening skills and help them improve. Why? Well, it's because engineers listen more than anything else they do. From our estimates, around 25% of the time, engineers are listening, whether it's on the phone, in meetings, talking with people, listening to people giving them instructions, or sharing information. And I do tell students that of all the information I've acquired in my career, by far the most valuable information has been conveyed verbally and not in writing. And accurate listening has been the key to making use of that information. And what's more, good listening skills will help students get much more from your teaching. Is that not something that's important for you? I used to measure the listening skills of my students, and I demonstrated that they needed to significantly improve, and over a few weeks, students can significantly improve their listening skills. And one of the ways I do that is by suggesting that they take notes and create mind maps, an amazingly easy way to take notes. That's in my book. And here's a mind map of this talk. That's my notes. Whatever you would draw in your mind map would be different. But it's a way of remembering what was said, the connections between different concepts. And in my experience, having made a mind map of a lecture, you can recall about 90 to 95% of what was said. The next, another basic one. We take students' reading skills for granted. So again, let your students measure their reading skills and help them improve and practice with relevant engineering standards. Standards that are really important that they get to understand. This is the standard that we use for our air conditioners, the safety standard for home appliances. And again, the techniques that you use to do that are set out in my book. Another one is getting students to ask questions. Now here, particularly in South Asia and many other countries, I found that students are very reluctant to ask questions. But what I have found working with students in these countries is that they're really good at coming up with fascinating questions when they work as a group. So get them to divide themselves into groups. It can be just 2 at a time, 3 or 4 students. It doesn't really matter. And give them 3 minutes to come up with a question. At the end of the 3 minutes, they have a question on a small piece of paper and they run down to the front of the class. You end up with a pile of pieces of paper and you pull questions out at random and answer them. I find that this works really well. And the same picture, because this is really, as Richard and Rebecca would tell you, this is really another form of cooperative learning. I thoroughly recommend cooperative learning techniques, and this is the wonderful books, but this is one I found that particularly useful. Learning together and alone. I've used these methods in my classroom, and they improve learning, particularly amongst weaker students. And what's important is they improve the ability of the stronger students to teach the weaker ones. And one of the points I've argued in several occasions is that engineers do need to learn to teach. Much of engineering is all about teaching. And another good reason for engaging with cooperative learning techniques is that what happens in cooperative learning is very similar to what happens in real engineering workplaces. This is a photograph of a real engineering meeting. And I photographed these engineers for the title of my book, The Making of an Expert Engineer. They're actually involved in collaborative learning themselves. They're learning from each other. Next, item 8, some very surprising cost factors, particularly in a country like India or Pakistan, where I am now. It's really important to understand that goods of equivalent design, quality, durability, and performance cost more in low-income countries than in high-income countries, as a rule. There are always exceptions. And I've given you examples. The next is labor costs. So it's really important to understand that labor costs are often higher in low-income countries because of indirect costs and low productivity. What counts here is the need for training, supervision, and logistics support, and it's not intuitively obvious. I've given you examples such as water supply. Electricity, for example, in Pakistan is 3 to 4 times more expensive at the point at which it does useful work. That's not the same as the price on the meter. It is the amount of money that you actually have to pay out in order to get electric energy to do something useful. And again, you'll find information on this in my book, Learning Engineering Practice. Again, that's easy to teach, and it needs to be reinforced many times. Now, here's a typical solution for an engineering practice problem. We've talked about the need for students to solve lots of practice problems. It's really important and really valuable, but we don't necessarily always have to place it in the traditional context. A lot of what engineers do is monitoring and checking work done by other people. So let's give them problems in that context. Here's an example of a problem solution. You can actually give the solution to students, and then you can say, well, what's the purpose of this solution? What's the accuracy with which we need to know the answers? What are the assumptions that have been used here? You notice, actually, this is taken from a paper on expert student and teacher problem solving. In other words, the teachers were considered experts and they compared their solutions with those of students. And neither the teachers, the experts, nor the students stated the assumptions that were implied here. Neither the teachers nor the students put a scale on the diagram or provided actual dimensions. And neither asked the simple question is, how sensitive is the solution to errors in the input information? And you can deliberately leave things out, like in this one, leaving out an important dimension and see if the students pick it up. So you don't have to leave it out all of the time. But the important thing, the idea here is that you give a solution instead of a problem. And you simply say, check this to see if it makes sense. Get them to identify what's missing. And of course, you can also make deliberate mistakes in the solution steps. And you can ask students to provide the reasoning why. Why did the solution follow these steps? So that's giving them the same practice problems, but by putting them in a different context, you're making it more realistic and much more representative of what engineers actually have to do in the workplace. You don't have to do it all the time. But selecting a realistic context helps students understand that these problems are important and are valuable, and that they will apply this knowledge in their practice, but they may not realize it at the time. Help them appreciate that they'll be doing a lot of checking of work done by other people. Here's another fun exercise you can do. And it's really important conceptually because it dispels the notion that drawings and specifications provide an unambiguous description of what's required. It's a very simple exercise. Get the students to make simple models. They can use Lego, wire, cardboard, glue, anything that's constructible in a reasonable time. The students make a sketch of what they've made, as I've shown here. Now what you do is you supply those sketches to other students. And the students then work from the sketch they have received from you to reproduce the model that the sketch represents. And then you'll have a lot of fun comparing the original model with what is actually constructed from the sketches. Almost invariably, what you'll find is that the reconstructed models will not match the originals. And this helps students understand that engineering diagrams and representations are reinterpreted by other people who see them differently. And consequently, one of the really important things in engineering is to check that when diagrams and written instructions are reinterpreted by other people, that the interpretation is close enough to what was originally intended, that the results will be sufficiently close to the intentions, that the ultimate performance will be achieved. Another exercise that students can do is to observe engineers and other people. I think I've got the numbering wrong here, I'm not sure. Why? Because we want them to observe culture, and in particular to understand that things like clothes, language, speech, skin color, the tone of voice, the social connections that a person reveals, the family, the tribe, the broderie or brotherhood, these are the things that distinguish culture and distinguish people, and they affect the way that people interact with each other. They also constrain agency. So these are the things that influence the way that work is done in the workplace and ultimately constrains the way that information is shared in an engineering context. So what I'm asking you to do here is to raise awareness of culture. This is really difficult when you only live in one culture. It's really difficult to see how that culture affects the way that people interact because it's something that's so fundamental that you see it every day, you take it for granted, you don't even realize that it's there. It was only when I was exposed ultimately to South Asian culture through my marriage and my long visits working in Pakistan and India that I became aware of this. But of course, for students who don't have that option, they don't have that possibility of being immersed in another culture to see it. It's much more difficult to help them understand, but it is possible and really, really important. If we're going to get on top of this issue of helping young engineering students become effective engineers in the Indian context, we have to do this. Remember, clothes, language, skin color, tone of voice, social connections, family, tribe, broderie, and the word that means brotherhood, but I can't pronounce it in Sanskrit. Remember the supermarket. Remind them to open their eyes to the influence of physical infrastructure. Remember to observe the street market and compare the street market with the supermarket. The supermarket again. And then this, probably the most important, ultimately, help students understand how to find paid engineering work by networking, exploring supply chains, studying relevant engineering standards, understanding local material costs, and simply persistence and keeping notes of what they do. This is something that at universities is not well done. And so far, after 20 years of disseminating the technique that's in my book, no one has ever written to me to say that it's failed with evidence that it has failed. So I encourage you to help your students understand that. Now, if you're interested in learning more, here's my website. And this very informative video that I found a few weeks ago, what do I do as a mechanical design engineer? And look at the diagram on the right. 50% of the time in meetings, 25% of the time documenting, So that's 75% of the time on socio-technical interactions with other people, and just 25% of the time designing, which includes searching for information, which is typically about 10%. So lastly, I'd like to tell you a little bit about what I do in my professional life, what I do most of the time these days. I taught engineering full-time at UWA until 2016. And then I stepped sideways and became an entrepreneur to commercialize an invention which I came up with indirectly from this research because I was exposed to the high summer temperatures in India and Pakistan. So it's a device which provides universally affordable air conditioning with about 5 times less energy consumption and about 5 times less climate impact. And the whole aim is to help improve productivity. If you look around the world, hot countries tend to be countries with low productivity. Surprise, surprise. And then you realize that people in India, Pakistan, across South Asia and other countries are working and living in conditions which for several months of the year are significantly outside the limits of human physiology as we know it, particularly for sleeping. It's no surprise that productivity is low in hot countries. And the hot countries that have managed to lift their productivity, all of them have relied on traditional air conditioning. But we can't do that for 4 billion people because we would literally cook the planet. And so this machine, a really simple idea, a tiny fridge with a fan. Simply, we cool people, not buildings. And to my knowledge, it's the only technology which offers today, available today, which offers affordable and sustainable cooling to billions of people. We think that the best way to disseminate this idea is by commercializing the technology so that it sells itself. And that's what I've been doing for the last few years. But in essence, it's all about people helping to be more productive. So thank you very much for patiently listening to me for the last 60 minutes or so. And I really look forward to your questions. And thank you for, again, Krishna, for inviting me, and for Richard and Rebecca.
Wonderful, wonderful. Big round of applause for James Trevelyan from everybody. Thank you so much, James. We will take some time for questions, obviously. Let's follow 2 channels, two ways of how we can communicate with you. One, of course, if you raise your hand, I will recognize the persons in the sequence of the raising hands, and you can ask your question and interact. The other, of course, through chat, because those of some of you might not be very convenient to unmute yourself. So either way is fine. So let us spend some time on having a dialogue with this very intelligent, very interesting person that has been with us for the last 1 hour.
Perhaps we should get them to work together in groups, Krishna.
I'm sure that.
Okay, we have a hand.
Okay, we have Jyotsna Cherakuri. Yeah, please go ahead and unmute. You're applauding. You're not really saying you have a question. Okay, so question from Devraj. Okay, you can unmute yourself, I think, right? Go ahead. Yeah.
Good evening. I think what James was suggesting about doing an activity-based classes, maybe some of the things where we impart the education system. But at the end of the semester, we have something called as maybe the semester and examinations. Once again, memory-based thing. And scoring the marks in that, once again, it's the big thing. If you score, you are eligible for placement and all. So what students, most of the students, they think is like, whatever I do, it's gone waste. So what at the end, I have to do well in the examination. So can something be done so where we can change the examination system where more weightage is given for the activities they do, maybe a little bit of weightage for the end semester examination. Until this big change is done, I think that the education system, I think will have a maybe a lot of things. I think going forward, we need to look into this particular aspect.
Well, thank you for asking that question, Devraj. And look, you're right. Students do have to pass exams. We have to be confident they actually know their stuff. And the other aspect, of course, is that this system of individual grading is also driven strongly by parents' expectations. Parents want to see a number. They want to see a grade for their students because they think that that's the grade, that grade is going to get them somewhere. So we have to be conscious of that. Parents, after all, are providing the money that employs us. So yes, but the trick is how we get students to learn enough so that they can pass the exams with confidence. And what I found in my classes is that the more students are active, that is, the more they're talking and making noise, the more excited about what they do, the more they learn. And you know, there are many other techniques which I've used, which I haven't talked about here tonight. But what I found in practice is that active students who participate, and particularly the shy students, it takes a few weeks for them to get used to this. They actually then learn stuff much better. And so passing the exams is so much easier for them.
Okay, thank you, Devraj, and thank you, James. Richard, do you look like you're ready to ask a question, or should I just read out some chat messages?
So perhaps, Krishna,
go
I
ahead.
could just continue that. Oh, Richard, okay, you want to ask a question.
Richard
Go
wants to
ahead.
ask. He's got a physical hand up, not the virtual hand.
Okay, well, let's see. When I went to school, which was somewhere back in the late Jurassic period, the faculty had several characteristics. Pretty much all of them in chemical engineering had either been in industry and had spent years working in industry as engineers, and then they came and joined the faculty, or they had extensive consulting experience. So they spent a great deal of their professional careers going out to industry and helping them solve their problems. Over time, as my career developed, those people left. They died, they retired, and they were replaced with fresh young research scientists with their new PhDs, to the point now where most engineering faculties are made up of people who have never really spent much time at all practicing as engineers. They're really research scientists, and their grants and their research publications are more science than engineering. How can faculty who have never practiced as engineers and really know from personal experience what engineers actually do, how can we teach that to our students?
That's a very good question, Richard. And look, the first thing I would say is if you go back and read the Grinto report, 1955, produced by ASEE, what you will see there portrayed very, very eloquently is the failure of a system which relied on practice knowledge. So up until the 1950s, engineering was taught by practitioners. And the weakness that was perceived in that system was that the students were unable to apply advances in maths and science, which had occurred in the previous decades. And we have seen over the subsequent decades how effective that change has been. Because we teach maths and science in a way which enables engineers to apply, you know, not only the stuff they learned in school, but also much more recent advances that occurred after they left school. That's underpinned the advances that we've seen in technology around the world in recent decades. So we have to accept that the vast majority of people teaching engineering don't do it. And this is where I think lies the challenge for engineering practice researchers, which is to provide an understanding of engineering practice which can be read in a short time and digested by ordinary frontline faculty who are teaching engineering. What I've tried to do in this talk is to at least give you an outline. And I think even with the measures that I've described in my talk, those can go a long way towards altering perceptions. And perhaps one of the most powerful techniques is this issue of observing real engineers. Because once you, as a teaching faculty member, once the students understand that you do have some idea of what it is to practice engineering, albeit through your own secondhand observations, which takes a little time, and you can do it through the eyes of your students too, and get them to interview engineers and then bring those accounts back to you. That gives you a measure of authenticity, which greatly increases the respect that students have for your teaching. They'll listen much more to you, whether you're teaching dynamics or circuit theory or whatever, because you can give them that touch of authenticity. So I'm quite sure that we can do much better with a relatively small amount of knowledge, but the key to it is to provide it in a form which makes sense for frontline teachers who are time poor.
Fascinating, fascinating discussion. Okay, any follow-up, Richard, or should we look around for other hands? Okay, Vijayendra, come in, please unmute yourself and speak. You have your hand up, so I'm assuming you want to ask a question or speak. If not, we'll have to, or maybe if not, I'll assume you're not having difficulty unmuting yourself. Meantime, okay, there we go. Kiran Chakravartulu, can you unmute yourself?
Hi, good evening. Thank you, Professor Krishna Vedula, and thank you, James, for the great lecture.
Kieran.
Hi, so I posted this question in the chat box, but I'll read it out anyway. So, engineering institutions, education, and practice themselves, we are now talking about breaking silos and working across departments. But then engineering itself is it has broken away from the society, in my opinion, and we are in our own silo as engineers. So if we try to bring these social interactions into the curriculum, into formal teaching, we are kind of defeating the purpose of actually getting out there into the society. We are actually bringing the society or social interactions into the building. So how do we actually solve this conundrum or address this conundrum?
How to do that?
Yeah.
So, well, Kieran, I think the first thing is to help students understand the education process. Because education happens in classrooms, even online, because of social interactions. We talk with each other. We listen to each other. Students talk with themselves. It's not something that happens in isolation. And many education theorists would be happy to explain this to you. So it's a question of opening students' eyes to what's happening around them. Then they can see that they are learning because of social interactions. You know, one of the most fascinating things to me was to observe, albeit at a slight distance, because my wife is still teaching, to observe what happened in education as a result of the pandemic. When students were isolated and restricted to their homes in many instances or wherever they happened to be, and they couldn't interact with each other. They interacted with the teachers through Zoom like we are tonight, but not with each other. And the effect on learning was catastrophic, because the reality is that a lot of the learning that takes place in our classrooms happens because students talk to each other, and not just in class, they talk to each other out of class. Students learn far more from each other than they do from us. They learn it indirectly. So helping students see that process is terribly important, because you can say, well, that's exactly what happens in engineering practice. You know, many young engineers are scared witless when they graduate, because they think to themselves, I can't remember anything that I learned. And they get really apprehensive. But we need to help them understand that once they get into workplaces, they'll learn from other people around them. And it's not a question of learning so much from them, but getting them to help. You know, one of the things that I've also observed among students is that some of our strongest students are not necessarily the strongest performers when it comes to actual engineering practice. As I said, grades, we know from well-established studies that grades don't make any difference when it comes to actual career performance. Why not? Well, one of the reasons is that the weakest students in the class have managed to get through engineering by getting as much help as they can from their fellow students. And that puts them in an immensely strong position when they get into a workplace, because they know how to get help from other people. On the other hand, the students who sail through our exams with hardly any effort at all and don't need to ask another student how to solve a problem, they're the ones that are going to find it really tough when they get into workplaces where they need to get other people to help them. So that's my suggestion. And that's why I've said, you know, get students to observe what's actually happening around them. Make them aware of what's happening in their schools. Make them aware of all the social interactions that happen, not just in the classroom, but also outside. And of course, also amongst their family and others too. Get them to observe what happens. And by opening their ideas, you can then help them understand that the social aspects of engineering are critical. And that's what will determine more than anything else their career performance.
Fascinating.
you.
Elsie, looks like you are raring to say something. You unmute yourself.
Well, thank you.
Next.
I'm delighted to be here. And actually, I would like to reassure everyone on this call that the same issues that you're grappling with here are right now being discussed in a 3-day summit at Oxford University. It's online, around the economics of mutuality. The same issues of making our professional activities relevant to the lived experience of humans is what business is also grappling with, and what I hear in this conversation. I've just ducked out of that summit because, James, my experience of you is that you are a creative person who always, when I listen to you, shares counterintuitive insights that move things forward. So I ducked out of that summit. It was headed up by Paul Pullman, the well-known, illustrious figurehead who is espousing a more contextual role for business in society, in alignment with the reality that we live in a living system. And our professions, unfortunately, have maximized for abstract outcomes that are hurting us. And I hear the same thing happening here. So I suppose my question is, and I kind of bridge, I want to see business be more effective in enhancing the well-being of humanity, in the same way that you talk about engineers might think of their work as enabling people to do more with less as a way of enhancing the human experience. And my question is, where and when do and can the engineering professions and educators come together with the business people who are grappling with the same issue? Do you see a forum where that's happening? Because once again, we're in our silos trying to address a systemic problem and opportunity.
Well, thank you for a very challenging question, Elsie. And I do remember, I think, talking about this with you before. Your name definitely is familiar to me. So, and thank you for bringing in those discussions from Oxford at the moment. Yeah, you're quite right. Look, I run a business myself. And our business works because all of our staff remain direct contact with our customers. And I emphasize the importance of this. No one is immune from the need to talk with customers, particularly when they're having problems. But in large corporations, it's a really difficult challenge because you're quite right. You do get silos. And if there's some really fascinating sociological studies. Just the last few days, in fact, I've been reading a wonderful PhD thesis, and I can share the reference with you later, written by a woman in Chennai, describing the work of water supply engineers and their interactions with other people. And there's some fascinating remarks there made by a young engineer who said, in this city, we have two major kinds of districts. In South Chennai, we have districts where there are wealthy people, powerful people who live. And in North Chennai, we have a lot of poor people. And the essential difference that we face as engineers is that in the south of the city, we are scared of the residents. When the residents make a formal complaint, either to us directly or to our bosses, we know that we have to respond. In the north of the city, the residents are scared of us. And they know that when they make a complaint, we will say, yes, something will happen. But we know and they know that actually nothing will happen. So there's been wonderful work done on this, and it is a real challenge, but I think through the education process, we can make students much more aware of this. And simply the answer is this, that when you create value for people, when you answer people's needs, money is never an issue. People will pay sometimes astonishing amounts of money for something which satisfies their daily needs. And there's no better example than drinking water. When you see what people actually pay for safe drinking water, you realize that there's huge business opportunities in reducing that cost, and they will transfer some of that cost to your benefit, and hopefully a lot of benefit to the rest of society as well. So there's lots of interesting discussions that come on that, because ultimately when engineers create benefits, of course, there is a discussion that goes along with that and say, how is the benefits going to be shared? And that's a question of social justice. And I know that some of my colleagues like Caroline Bailey and others have been introducing ideas of social justice into engineering schools and finding how enthusiastically the students respond to these discussions, the opportunity to have these discussions and to talk. So you don't have to set aside very much time. You know, in fact, we all know that the less you teach, the more students will learn. So just setting aside time every now and again for some interesting philosophical discussions, helping students open their eyes, is immensely valuable in the education context. And the more they get excited by these ideas, the better engineers they'll be. So thank you very much, Elsie, for asking that question.
Okay, we have a couple of hands up. Let's quickly go through them. In the meantime, maybe James, if you see something interesting in the chat box, you can do that, and then we can close it up.
Hello.
Yeah.
Hello.
Yeah. Let's go
Hello.
to Wahidullah Azizi. Oh, Vijayendra, you finally got you unmuted. Okay, go ahead, Vijayendra.
Yeah. Thank you, Professor James, and thank you, Krishna, for giving this opportunity for us. I've been teaching civil engineering from past 30 years. Of course, I've gone through various changes I've seen in the education policies, right from 1990s to 2020s. Of course, we struggle to accommodate ourselves to these changing scenarios, particularly with respect to teaching. Of course, at the core, we remained more or less same as what Professor James was trying to convey to us, but too much of interference is also happening with respect to teachers, thereby there is, particularly for young teachers, there is a lot of problem in adjusting itself for these changing education policies, education methodologies, and so on and so forth. And what I observe, particularly after this accreditation and all that picked up in 2005 onwards, two things. One, there is a drastic difference between Indian and Western technical education system, particularly right from the what is the intake, the centralized system, examination system, how the evaluation system, all this is entirely different, and also the teacher's background with which the future generation is being taught is also entirely different. The second thing is the Western countries, they're coming to practicing engineering. I'm aware that this civil engineering practice, as the James showed in many slides, there's a drastic difference between how the civil engineering is practiced in Western countries and in India, or for that matter, whether it is Bangladesh or Pakistan. The reason is the engineering profession, particularly civil engineering, is not at all looked upon as a profession at all. Like what it is being with the doctors, lawyers, and architects in India. They are more professionally trained before they come out of the engineering college, technical schools, okay, compared to our
keep this short, Dr. Vijayendra?
Yeah, and finally, there is obvious reasons that our students, how to sensitize our students to social problems and relate their technical background to solve those problems. They see that, but they're not sensitized for really looking into those problems in an engineering sense. Yes, we can solve that problem. Always they look at that as any other common person rather than as engineer. Thank you.
James, any quick comments, and then we can
well, just a quick comment. I mean, Jayarendra, what you're really talking about here is the influence of social culture. And I know that it's a difficult subject, but I've tried through my illustrations in this talk to give you some examples which you can then relay to your students and explain the differences. And really what you need to hold in front of you is, and I know that this is in my other book, The Making of an Expert Engineer, is that there are engineers in India and Pakistan and other countries who have managed to figure out how to create immense wealth for their employers. And it's not rocket science. And as long as students know that this is possible, then that gives the inspiration to realize that, yes, I can do things here in India. I don't have to travel somewhere else. Yes, of course, it's different. I have to learn different things, but I can do it. Others have done it, so therefore I can do it. So really, I think that what I'd ask you to do is to get hold of my book, The Making of an Expert Engineer. And if you're really struggling, then if you send me your mailing address, then I'll send you a copy from Pakistan and hope that it reaches you in India.
Hey, thanks, James. Is Hans Hoyer still here?
I might have to send it from Australia.
Not
Yeah,
even
yes,
taken.
Krishna, I'm still here,
Yes,
but
yeah,
I
it's
wanna,
time for you to, sorry, Wahidullah and
I-
Amel, we're not able to get to you,
Are
but
you-
please keep in touch with us. Send an email to me or James. The recording of this will be available on Canvas. And if you don't have access to Canvas, just send me an email or Sridhar an email. You'll be on Canvas, and in the interest of keeping on time, I'm going to let Hans the closing remarks.
And Krishna, I'll just quickly say that I will endeavor to answer the questions in the chat. So if you can make sure that I receive those
I
questions,
will
I'll
send you
write
the
some
chat.
answers.
I'll send you all the chat.
Thank you.
Yeah. Sridhar will do that.
thank you very much, Krishna. Just give me a second here.
Yep. we can see your
Greetings,
forehead.
everybody. Can
We
you
can
can
see-
you hear me, Krishna?
Yeah, we can see you. We can see your forehead, and we can hear you.
James, I really want to thank you again for this very thoughtful, provocative presentation. It's very, very special, and it underlines the importance of the special series that Krishna and I, and now in close partnership with Richard and Rebecca, are facilitating at a global level. I'm very, very excited about that. My role in partnership, of course, with Krishna and the IUC in India is I lead two global organizations. We have several leaders that are present here of both IFES and the GDC. And I just want to make a couple of comments in terms of our work, because we have several leaders of our organizations here, but many of you don't know us. One of the key things is I'm very pleased that we will have our first regional conference in Tirana, Albania next month, bringing together the engineering, education, academic, and corporate community in that part of the world that many of us have historically had very limited. I myself, as a Berliner, know very little about Albania and its surrounding countries. And for us to connect with that community in that region is very exciting, and I will facilitate connections. Secondly, I'm now working closely with our friends in Asia and the complexities we all know of COVID the last few years. Again, have our regional Asian Deans Conference in Hong Kong, without going into details on that. I know we have some deans here that would be interested to connect, and India has participated since I helped form this about 11, 12 years ago. Working very closely with our friends and colleagues in Monterrey Tech in Mexico, our global conference in October. And a key thing, building on a very successful conferences we've had, and particularly just recently, also in Cape Town and in others, is the engagement of students. It's not only the faculty, the deans, corporate representatives, but the students are very, very important. And we are working, and I'm currently in discussions with good friends and colleagues in India, for example, to bring Indian students to Mexico, thereby cultures that don't have much connections through many, many ways can get to know each other. We would talk obviously for a long time. Just very, very briefly, and we have a couple of our co-authors here. We've been working over the last 3 years. Women engineering leaders have been writing several journals, books of our Rising to the Top series. Professor Kharija from Malaysia is on this call here. Professor Debbie from South Africa. Sushma Kulkarni led the book on India, that of Rising to the Top. I just want to bring to your attention of these very important efforts, and we are working now on the MENA Arab world over the next few months to again bringing women engineering leaders, corporate, governmental, of course, academic and so forth, NGOs into that journey. So with that, we look forward, Krishna and I, to engage all of you as we move forward in our webinar series for the remainder of this year. It's a real pleasure. Again, James, thank you for your very thoughtful presentation. Thank you kindly. And peace and be with all of you, and above all, stay healthy, please.
Thank you, James.
Thank you, Krishna.
everybody, for being
And
part of
thank
this.
you, everybody.
Okay, good night, good morning, good afternoon, wherever you are. Be healthy. Okay, take care. Bye. Signing off.